John Hopkins APL, and this talk is matched up with a previous talk in that he's also going to be talking about graph stuff on Accumulo, a little bit different take. So, like I said last time, graph is a kind of quintessential use case for Accumulo. It's really good at it, and I'm glad to see it advancements of this. So here's the talk. The other thing I want to mention is after this talk is our lunch break, which is an hour. So at 12:35. Lunch is served at the end there where the breakfast was. The only thing I ask, there's not room for 330 people in that room. So if you don't mind, like, spread out a little bit, either find somewhere to sit down or you can come into these rooms and eat in these rooms too. Okay, thanks.
Good afternoon, everyone. My name is Ryan Webb, and I'll be giving you a talk on our TinkerPop blueprints implementation that's backed by Accumulo. So for the agenda for this talk, first I'm going to give you a quick introduction to the TinkerPop's API, our detailed implementation, and how we solved some of the problems we had, the obstacles we faced with the TinkerPop implementation, with the TinkerPop API, and the rules it makes you enforce, how we overcame those obstacles, our MapReduce integration, and some performance numbers. So just some background. I'm an associate professional staff at the Johns Hopkins Applied Physics Laboratory. I have a bachelor's in science and computer science from University of Delaware, and I'm currently pursuing my master's in computer science at the Wayne School of Engineering. So TinkerPop is a very simple, or TinkerPop Blueprints is a very simple API that's the foundation for the entire TinkerPop stack. The TinkerPop stack encompasses a graph server, which gives you REST access to your graph, a graph algorithms engine, object to graph mapper, a traversal language, and a data processing framework pipeline. It has the blueprints itself, has an extensive test suite to make sure that implementations pass the required rules it needs. It has a very simple API that is also served up in multiple interfaces, so you can extend the functionality you need for your API, or limit the functionality you want to give to a user through these APIs. So here's a UML diagram of the TinkerPop Blueprints API. So we have in yellow the TinkerPop's API, and in blue our implementation. So you can see there's the master graph interface, which these other sub-interfaces extend, with indexable graph, key indexable graph, transactional graph, read-only graph, and a batch graph. These all have their own sets of rules and implementation details that the implementer have to take care of. We have Accumulo graph, which implements both indexable graph and key indexable graph. Key indexable graph gives you the indexing that you're used to. You have a vertex with a key value property on it. You can index on that. Indexable graph gives you a different kind of indexing, where you build your own index with key value properties and say that vertices are part of that index. So you can traverse your own indexes as you build them. This lets you give you different views of your graph dynamically as you want. Batch graph gives you a way to load a lot of elements into your graph quickly, but it has some weird, funky rules in it. So we decided to hold off for the first cut, our batch graph implementation, but we have a bulk ingester which follows the API pretty closely, but not the rules that it requires. And then in the actual element side, we have vertex and edges and direct implementations of those. You can get properties and the adjacent edges or adjacent vertices from these elements. And then we also have MapReduce vertices and edges that have their own rules about how much access you can get back to the Accumulo. Because if you are going back to Accumulo in every vertice in your mapper, that can get really expensive. So we try to make sure that we give you all the information we can. And if you have to go back, that's your decision. So here's a look at the API using it. So this is using our Accumulo graph. And except for the first line, it would look the same for every implementation of TinkerPop blueprints. So you make your configuration object, which sets some parameters. And here we have the basic ones: what instance, what user, the password, name your graph, and your zookeeper. You pass that to the graph factory, which is where you start entering the TinkerPop API. And then you get back a graph. On that graph, you can add vertices, you can set properties on those vertices, add edges, and add properties on those edges. Very simple. So as we went to implement these functions, we faced this spectrum of trade-off. On one end, you have a high-performance system where you can write and read as fast as you can. Things always happen eventually. If you have multi-users, they may have different pictures of the same graph. And on the other end, where everything's consistent, we write out as much as we can, as often as we can. We make sure that when two users are using the system, they have as close to the same image of the graph at the same time. For our TinkerPop implementation, in order to pass the unit test, we had to go to the far side of the spectrum. We had to be as consistent as possible. Every time you add an edge, it's checked to make sure that it exists, and if it does, we throw an error. Every time you add, and then we write out the edge, and every time you add a vertex, we check to make sure it exists, and if it does, we throw an error, and then we write it out if it doesn't. So that's very expensive to go out to your graph and check to make sure a vertex exists or not, and if it doesn't, then we can do our write. Our table structure is broken up into, we have an edge table, a vertex table, we have an edge index table and a vertex index table, and then we have a metadata table, so you know what indexes are created when you first load up your graph. Here's the table structure for the vertex and edges. So it's very simple. We have in the vertex table, the first row is a exist flag, because you can add a vertex without any other information, so there has to be some way to know that you've added a vertex. And then in our edges, so connections between vertices are in the next two. So you have a vertice with its in-vertex column family, and then you have the out vertice that it goes to, and the edge that represents that relationship. And then in the value is the label of the edge. So an edge label is something that is required every time you make a edge with in the TinkerPop API. It defines what that edge is. So by putting in this value, it lets us scan just through the vertice table and do some of the API calls without having to jump to the edge table for another scan. Similarly, in the next row, the out vertex, we have the other vertice and the edge that represents that relationship and its label, and then properties, row ID, column family, and then in the value field is your serialized value. Edges are very similar, except in its existence clause. So an edge has to have an in vertex and an out vertex and an edge label. So that's all mushed into one line. So we have the edge label, its label flag for that column family, which is just a static, the in ID and the out ID of the two vertices on each end of this edge, and then its label and the value. And then properties are just off that, just like vertices. So for graph access and index creation and use, it's very simple and almost transparent to the user. So you have your graph access at the top. We're just going to iterate over all of our vertices and get the property name. Easy peasy. We're going to cast our graph to a key indexable graph, which gives us the functionality of using the key indexable features, which lets us create a key index on name for class vertex. And then once that's done, we can iterate over the vertices again, and it should be faster because now name is indexed and we're using a quicker lookup method. So with the multiple interfaces, if you don't cast it to an Accumulo graph at the beginning and you want to use these other features, you have to do your casting to what features you want. So these are the tables that are created by the indexes. So in the index, it's a simple reverse index. We have the serialized value in the row, property key in the family, and the ID in the column qualifier. This can be an edge or vertex ID depending on which table you're in. And then the metadata just keeps track of the index name and what class it's over. So the obstacles we face with this implementation is that existence checking is expensive. If you want to add a few edges or a few vertices and edges to your graph, you have to go and make sure they're not there first. Writing every graph object out is expensive. If you want to add edges, you have to make sure they're written to Accumulo before you can add the next one. Building indexes post-ingest is expensive. It's a blocking call, full table scan to make sure you get everything. If you add the index before you start your ingest, it'll just be done automatically. So it's learning the API at that point. And just overall, consistency is expensive, which we know. That's a thing. So we overcame these obstacles by giving more power to the users who know they're using an Accumulo graph. So if you just stick to the TinkerPop API, you can use it and it'll be fine. You'll have fine performance for small scale, local things. You'll have fine performance for web access to the database. But if you want to do large scale processing, you want to use their specialized or the specialized configuration you can offer to the Accumulo graph. For ingest improvements, we give the option to disable existence checks. So if you know that the data you're ingesting might not be there, but it will be there eventually, you can just write it out, and we'll just write it out, and hopefully when you were right about your assumption. Right now we don't have a validator that goes through and makes sure, all right, does every edge exist? Does every vertex exist that you say should exist? But that wouldn't be too hard to implement, it's just not done yet. We allow for manual batching. So you can turn off the auto flush mechanism with a simple call to the configuration before you make your graph. It will stop its auto flushing, and it will batch up your mutations before it writes them out to things you can also specify, the batch size and the amount of writers. All those things are in the configuration object for you to choose. And then we also provide the specialized ingest path of Accumulo bulk ingester, which does the minimum amount of work we have to do and to get our results in, and does it as fast as we can. So this is the best way we can get stuff in. And then for traversal improvements, we offer attribute preloading. So you can specify, I want the name attribute preloaded, and I want an image preloaded. So when you go and get that vertex, and then you go get those properties, they'll be there in memory. One benefit of this is if you have a large value in your properties that you particularly don't care about all the time, you don't have to get it. You don't have to waste that bandwidth to get that property into your memory. Property catching, so if you access a property, it can stay in memory for a certain amount of time that you set. Same with element caching. So if you go to get a vertex, you can say, I want vertices to exist in my memory for 30 seconds or 10 seconds or whatever you want. So here's the API for our simple bulk ingest. It's initiated the same way with the same configuration object you used before, and its API is a little different. The property builder class is a class that saves on the mutation of adding properties to these vertices, so it just builds on the mutations we already have instead of making new ones. But it's very similar, and it does it as best as we can with no consistency guarantees, none of that. It just goes. And then our MapReduce integration is something we really wanted to offer. Sure, you can write these things on a single user API, but we want to view our whole graph, and MapReduce is an easy way to do that. In your tool, you just set your input format to be a vertex input format, and then you set the graph configuration with the same graph configuration object you used earlier. And then in your mapper, you get a text with the ID of the element you're currently mapping over, and the vertice that's represented by that ID, with all the information we can get about it. In the future, we're going to extend the attribute selection to MapReduce also. So if you don't want to get your image when you're mapping, you don't have to. So some results. We had an 8-node cluster, 64 gigs of RAM, quad-core processor, 2 4-terabyte drives, 1 gigabit networking with Accumulo 151, and Hadoop 2 running MapReduce 1. Note, we just set up Accumulo. We didn't care about the configuration, so the configuration's really terrible for the amount of RAM we have. We're nowhere near using all that RAM. So these numbers would scale appropriately. And then the data set we're using is the Friendster Snap database graph, which is 65 million vertices, 1.8 billion edges, no property data. And then for our ingest numbers, scale pretty closely to the numbers you want. As we doubled our nodes, we got half the time. And then in the vertex iteration, we got perfect scaling, whereas we doubled our nodes, we got half the time for vertex iteration using our MapReduce. In the ingest path, that was using our bulk ingester and a mapper. So we spun up 8 mappers, or no, I forget how many mappers, but we spun up mappers, each with bulk ingester, ingesting their part of the graph. So in conclusion, what we have is a simple, easy-to-read graph API. It gives developers a lot of tuning points to improve the performance to their use case. Performance is good enough. There's minimal overhead compared to Accumulo input format. Our vertex input format is practically the same. There's minimal for object creation, but it's practically the same. It's not meant for high-performance specialized solutions. So if you have a problem and you know your data and you have a specialized interface to it, don't use this. Use your stuff. It's going to be better. This will never be better. It's quick to develop new ideas and investigate your graph. So you can have people who've never heard of Accumulo. You just give them a configuration file and say, here, use this, and now use this graph API and look at this graph. Tell me what you can find. And so they never have to know how Accumulo works or how any part of Accumulo is managed. They just access a graph like they would access a graph. And it's easy to integrate, and it's already integrated with several products. So since we implemented TinkerPop blueprints, we get the TinkerPop stack for free. It is low effort to get REST access to your graph if you implement this API. You run a script, it spins up Rexter, which is the web server, and then you can hit a URL and get vertices, get properties. You can exploit your graph in numbers away. At the lab, we have a UI that already runs on TinkerPop, so we could slide this in underneath that and have a UI to look at our new graph. Future. So polished and open source, that finished last night. We are now open sourced at github.com/jhupapl/accumulograph. It's rough. It just got open source. Documentation is the code examples you saw in this presentation. We'll be improving it over the next week, get the documentation better, and then start adding the features we need and want to implement. We want to investigate the use of iterators for our index maintenance. We did some exploration on the possibility of using cross-table iterators, but the conclusion is that it's not worth what you get from it. So we might not be able to use them, but we still want to spend some time and investigate that area. Using locality groups for indexes. So if you make an index over name, or even just labels, labels should probably be in a locality group, so they're quickly to iterate over. Addressing security. So other than you providing us a user and password, we don't really interact with the security of Accumulo. We need to. We need to investigate how we would stay true to the TinkerPop API, but yet provide the access to Accumulo security. Graph query. So with TinkerPop, it uses there's a default query interface, which or default query class that we are just providing. It's the default. It does things how it would if it wants to get a vertex with an attribute, it would go get a vertex with an attribute. Just call those API calls. What we have to do is implement our own, because we know our data. We're a little smarter than the dumb API. We can get through these queries possibly faster. Extending MapReduce integration. So right now, what you saw is what we have. We have a vertex input format. We want to extend that to an edge input format and output formats also. And then upgrading to Accumulo 1.6 and TinkerPop 2.5. The transition to TinkerPop 2.5 won't be that far of a stretch. There's like 2 things that interact with us in the changelog, and it shouldn't even matter if we upgrade. But we're still at 2.4. Upgrading to Accumulo 1.6 will give us some power that I hope to learn about later in a talk with conditional mutations. So conditional mutations let you write out a mutation and say, only let this write if another field exists. So that'll let us just blindly write things and not care about existence. The conditional writer will make sure that the vertex exists, and it will not set the property if the vertex doesn't exist. And hopefully I will learn more about that tomorrow and we can get this implemented. Or tonight, or yeah. And then table namespaces will help clean up the view of the Accumulo master. Right now it's just a bunch of your graph name underscore vertex or edge underscore indexes. The namespaces let you group similar tables together, so it's a little more appeasing to the eye. Resources. So TinkerPop.com is your one-stop shop for the TinkerPop API, which can give you, there's other implementations of the TinkerPop Blueprints API. There's an in-memory one, so if you just want to play around, you can just make a new Tinker graph. There's connections to JDBC. There's a Titan one. There's a whole bunch. There's a few of them. Ours is not currently on there. There's another one on there that is made by someone on our team, and this is an extension of that work, improving it. Once we polish up our API a little more, or our implementation a little more, we will forward this out to the TinkerPop people to get posted on the website. And then a resource for the database or the graph data we used. Yeah. Any questions? All right. Thank you.